So those were the basic routing algorithms we used, and now we'll go over to how routing actually happens inside the EDA tools. So remember that metal stacks are changing and growing. What we see is some sort of a representative layer stacks for 130 nanometer to 32 nanometer technology nodes. And what I just want to point out here is that you can see that in older technologies, what we have is just a bunch of metal layers which went and grew from 1 or 2 metal layers into 6 or 8. But they're the same type of thing. The height of the metal layers are the same, and the distance between them and so forth. And therefore the DRC rules, the minimum spacing, minimum width, was the same. But as we continued to progress, we wanted higher metal layers to be thicker to reduce the RC and provide better power routing and maybe clock routing. And then as we progress, we have what we call X, Y, and Z layers. So they're different thicknesses. And you see that the lower metal layers for local interconnect, the median layers for maybe clocking or longer global routes, and the top layers for mainly power connections. And it gets more and more complex as we go, and there are more and more routing layers. And you see that the top layers are really huge, and they're just used for power routing, and for maybe the lower, a bit lower than that, for the main clocks and so forth. Okay, so here we can actually see some photos of this. So here's a UMC 6-layer stack, and this is pretty equivalent for the different layers. Maybe you have some thicker layers up top, but when you get to the Intel 45 nanometer stack, you see that there's really a difference between the local interconnect lower layers and the global interconnect, and then the power routing on top. Okay, so we need to take care of this within our routing algorithms, and as I said before, this becomes more and more complex as we go on, and the tools become really heavy. Okay, so we start with global routing inside our tools, and we have to first say what our tracks are, what our grid spaces are. And a track is basically the minimum spacing between two metal layers. So we see here minimum spacing between 2 metal layers, and we have the minimum width of the metal layers. So what you usually do is we say that we want to put down a metal that it sits at the center of the metal layer, sits on this virtual like track, this point that we call a track, and we want to make sure that we can put another metal layer with a minimum width on the adjacent layer, and we won't have a DRC violation. So the size of the track is a metal width plus a metal spacing that causes the pitch between our tracks, and we basically lay out this track along our whole chip, and these are these points in this case on the x-axis, giving us these vertical tracks that we can actually lay down wires. Okay, so what we're going to do with global routers, we're going to take a certain number of tracks, let's say 10 tracks per layer. Now the tracks again can be different for different metal layers because our DRC rules are different. So we may have our tracks defined like this in metal 1, but on metal 5 they may be different. And we're going to take about 10 tracks per each layer and say that's going to be our G cell or our G box. And we're going to show here that we make this more coarse design for our global grid, and we're going to say we can now route the number of tracks we have. That's the number of routes we can do through each edge, and then we can do our maze routing to do our global route. So that enables us to do fast grid routing, fast maze routing through these global cells or global boxes. And when we do that, we're going to take in optimizations that are obviously going to minimize wire length, which we've discussed in our algorithms before. We're going to also try to balance congestion by trying not to have too many tracks go through each edge and try to balance that out. We're going to try to have it timing driven, so we can estimate parasitics and see that our timing critical wires get better, shorter wires. And we're going to have to also sometimes look at noise and SI, which we'll discuss in a few minutes, and maybe try to keep buses together. Okay, so this is done as the first stage of our routing when we actually tell the tool to route our design, but it's also used for trial route, which is done earlier in the flow. For example, during placement, we're going to run some trial routes to get better parasitic extraction and so forth. So this is really quick. Maybe we won't do all these optimizations inside, but we're going to want a real quick route, and so we're going to use this type of a global route and say that's enough. We're not going to fix any types of DRCs, but we want to get a picture of the congestion. So usually at the end of this type of a stage of a global route, we're going to be able to show our congestion map. We can usually get some sort of a heat map that shows the areas that we have higher congestion. And again, during floor planning, placement, iterations, we're going to look into that and try to fix those areas. We can look at different types of congestion reports, or in the way it's shown in ANOVIS, we can take a certain type of an edge here, and it's going to say what the congestion is in the vertical and in the horizontal directions. And if we have these large congestion areas, we better not continue to our detailed route, but go back and fix our floor plan, and replace the design and so forth to try and get lower congestion, or else we're not going to be able to route. So once we finished our global routing, we can start detailed routing. What we're going to do is we're going to take each of our G boxes or our G cells, and we're going to do track assignment, saying each net that's inside, where it connects to the next G box. We're going to give it a certain track that it has to meet, and then we'll set the source and target for each of these nets, and then we can go and do this detailed route, which is a more fine-tuned grid routing that actually takes each and every single one of these layers and connects it from the source to the target in a detailed way inside the grid box, inside the G box. But it's a much easier problem than routing the whole design. So we're going to assign nets to tracks, lay down the wires, connect the pins to the nets. Of course, solve the DRC violations, because in this track assignment we may be doing some sort of a rough type of a routing that has all kinds of problems left, and then really detailed route has to go iterate and try to solve all the detailed and complex DRCs. We also have to check if we have cross-coupling violations, crosstalk violations, and apply all kinds of special routing rules that we may have defined. So the flow is track assignment, then a type of a global routing inside the cell. DRC fixing inside a global routing cell, and continuing iterations trying to fix that. And you'll see that the tools, they tell you what type of a routing iteration it's going through on each of these cells. Okay, what kind of DRC fixes is it gonna apply? Well, we may have two nets that were laid down exactly on the same track. They're gonna be shorted together, so it's gonna have to put some spacing between them so they're not shorted anymore. We may have all kinds of notches that appear. So this is one case, and this is another type of a case of a notch. And DRC rules will tell us we're not allowed to have that type of a thing, but it may be left over as a residue from our iterations, and the tool may see that, look, instead of doing this type of an elbow over here, it could have just connected that directly and we wouldn't have this notch appear. Or in this case, we had some sort of a connection that went up to a via down, and we could have just had some small piece of a wrong way route, some sort of jog that would have solved that DRC violation and made life easier. We may have thin and fat spacing rules. So our tracks are based on minimum spacing rules, but then with complex routing rules, one of the things that happens is if you have a thick wire, you can't put it at a minimum spacing next to a thin wire, or if wires run too long beside each other. So these types of DRCs are going to be seen after doing our track assignment and our first iteration of a detailed route, and so we'll have to go and put some extra spacing between them. And finally, we may have all kinds of things, like when we take overlaps over our different via layers, we may have spacing violations that appear between the contacts or so forth. And one way to do that is just to offset them from each other so we don't get that minimum spacing violation. So these are just small examples of the types of DRC fixes that can be done in different iterations. Timing-driven routing, what does that mean? Well, we're going to try to go and optimize the critical paths. So we know from our static timing analysis which paths are more critical, and so we may decide to route those nets first to get them better, straighter routes with less RCs, and get a shortest path possible, not have all these problems of being blocked by other nets. We may actually go and manually assign net weights, so we can go and say, okay, this net is more important than the other, and the tool will go and route it first. For example, we may give a clock a higher net weight than other routes. Then we can go and apply fixes such as wire widening. If we widen the wire, we're going to reduce its resistance, and possibly the RC delay through that wire will be lower. And finally, if we have a congestion design, we may need to set the timing-driven effort to low, or we may not be able to finish routing at all. And in general, there's lots and lots and lots of options inside the router, and just beware when you change the default options, because you may make things happen that take your runtime to infinity, and maybe you will finish with a lot of DRCs and not be able to route your design because of it.